All right, starting in 3, 2, 1. Welcome back to Neutral Podcast. Thanks for joining us. We are in a new temporary studio just for the day, which is our fire testing for the Edison Project. And I am happy to be interviewing David Barber, who is the master behind the engineering and fire code for the test. Welcome to the podcast.
Thank you. Nice to be here.
Thanks for coming on.
Interesting situation.
Yes, it is.
Great location.
Yeah.
Great location.
Just before we get into what's behind us, just give us a little intro on who you are and what you're doing.
Yeah, David Barber, fire protection engineer or fire safety engineer. So I have been involved with timber and timber projects pretty much my whole career. And, you know, my aim is to basically help enable timber projects. So we want to be able to have more mass timber. We want to be able to have mass timber built safely. And, the aim here is to be able to try and assist developers like Neutral and others to be able to build the buildings which they want to, which use mass timber and use it in a way which meets codes, meets building regulations, meets standards. So my background really helps with that. I've had a structural engineering background in timber and then started to, be more interested in the fire side and have been involved with fire testing and the development of some ways fire codes and fire regulations through my career. And it's been an interesting journey because quite a long time ago, 20, 30 years ago, we didn't do a lot of timber buildings, did a lot of light timber frame, a lot of smaller timber buildings, whereas nowadays, especially in the last 10 years or so, mass timber has absolutely taken off, which is fantastic. So as someone who's been in that industry for a long time, it's great to see, and it's nice to be part of that journey, to be able to see timber go from being what has always been considered a very low-rise structural material to something which has grown to becoming a high-rise structural material. And it's a fascinating journey, fascinating process to be able to get to that point. So yeah, that's my background in some ways, and being able to be here today looking at a fire test.
Yeah, and you don't have a Texas accent, so
No.
Where are you from, David?
Originally from New Zealand, so and now living in Australia. And but previous to that, lived here in the US, worked in the US for nearly 8-9 years, and used to work in DC. And over that time, spent most of my time working on timber projects. And so at the moment we're here in Texas, here in San Antonio, in a nice, beautiful, warm day, in a nice warm building with a fire test.
Yeah, it's hot in here.
Yeah, it is.
It's like we're both sweating buckets right now, aren't we?
We're looking calm.
It's like, what's the temperature of the fire test behind us?
At the moment, it is around about 1400 degrees Celsius. So that is hot. And it'll get progressively slowly hotter. It's kind of just about at its maximum. We're about an hour and 20 minutes into the test. It goes up slowly from here, very slowly, but pretty much if you look at the graph of the fire test, we've gone a long way up the curve, and now we just kind of slowly increase over the next period of hours. And this is going for 3 hours. So that is something which is very new and has not been done before. So this is kind of, really cutting edge sort of territory.
Yeah. Give us just a little primer into what we're looking at. And for those viewing on YouTube, you'll be able to see this in the B-roll. But what are we looking at and what are we doing the test for?
Yeah, well, at the moment, I'll have a look as well. So we've basically got a beam and a column, which we're testing. So there's a column which is sitting in the furnace, the gray box, and you can see the sort of the orange glow inside the furnace there with the window open. And then the extended walls which sit above that, that is all the furnace. So everything inside that is the furnace. We've then got a beam which you can see the end of, and you can see a bit of flames coming off the end there. That'll continue to occur through the test. That connects into a column, and inside the furnace is actually a column. So we've got a full-size timber column, full-size timber beam, and then we've got a CLT floor sitting over the top of that, which acts as the lid to the furnace. What's around that is the blue frame, and that's what's called the reaction frame, the loading frame, and there's a loading jack, which is the orange item at the top there. And that item is basically applying a load. So we are applying a load direct to the CLT, which is applying a load to the beam. That's applying a load to the connection, which is sitting at the beam to column connection. And that is all being exposed. As I said, it's been in there for just over an hour now. we're taking that through to 3 hours, and that's part of a standard testing methodology which is carried out for all structural materials, whether this was steel or concrete. We have exactly the same testing process for all of them. So there's nothing different from a timber point of view. It's just the fact that this happens to be the first time that anybody has attempted to have a beam to column connection with mass timber tested to 3 hours.
Yeah, and I think a lot of times I get investors and other just industry partners asking, why are you doing all this testing, and hasn't this been done before, and doesn't the industry already have all this data that we can pull from? And the answer is no, we don't. We're kind of at the cutting edge of mass timber, especially at this height. But give us a little background in why we don't have any of this testing, why we have to do these tests to get approval.
Yeah. And a lot of that is just to do with the history, because in some ways the codes, not just the codes in the US, the codes globally, typically what they do is as buildings get taller, fire ratings typically get higher. So the levels of fire protection we need to put into buildings, whether that's detection and alarms, means to allow people to evacuate, firefighting aspects such as hydrants and other firefighting equipment, that all increases, and sprinkler protection, all those sort of things, water supplies, they become more resilient, and we put more of that in because the buildings are taller. So it takes longer for people to evacuate, and it takes longer for firefighters to actually get into the building to fight the fire if something goes terribly wrong. And so as part of that, the fire ratings increase as well. So low and medium rise buildings, where sort of potentially at, no fire rating, or maybe an hour fire rating, 60 minutes. As we get to sort of medium rise buildings, sort of 10, 12, maybe 15 stories, we typically at sort of 2 hours of fire rating, maybe 90 minutes in some countries. Then as we get to taller buildings, typically, maybe over 12 stories, it changes from country to country as to where that line sort of kicks in. We start to really increase the sort of fire ratings that we need. And it's a level of resilience. It's the level of safety margin that we build into buildings from a fire protection point of view, but also a structural fire protection point of view. And so the code here in the US, once we're over a height where we are truly high rise, we're at a 3-hour fire rating. And so that is slightly different to a number of countries, which often keep it at 2 hours or 120 minutes. And so for us to get to a truly high-rise building, we need to be able to have timber structures which withstand a 3-hour fire. And that is different. And it's simply because as we've grown timber structures, we have needed to continue to increase the amount of fire testing we are doing from 1 hour to 2 hours, and now we're getting taller structures. We need to actually go to 3 hours. So in some ways, the code hasn't changed. We're just slowly catching up with timber structures building taller and taller and wanting those buildings to occur, that we have to kind of catch up and do that testing to match what, in some ways, the steel and concrete industry has done for many decades. We're starting to do that testing as well. So we've got a lot of good 1 hour testing, a lot of good 2 hour testing, and now we're starting to get into that 3 hour testing, which is really kind of cutting edge. It's very sort of unique. And it's pretty cool stuff. Pretty good stuff.
And explain why for Edison, which for those not knowing, Edison is a 31-story mass timber hybrid project in downtown Milwaukee. So it's got 26 stories of timber. The rest of it is a podium structure, which is concrete. But explain why Edison is kind of out of this 2-hour fire rating or 1 hour fire rating, and where there kind of has been a lot of testing done, especially on the fire side.
Yeah, and that, in some ways, that kicks in after we get above 12 stories. And we're basically looking at a timber building whereby, from a construction class point of view, in some ways to think about it, we're at a very high-rise building. So our structure is at 31 stories, is right into the high-rise. And so there's always a debate about what is truly high-rise, and there's numbers in the code, and there's numbers about, in some ways, what architects think is high-rise and what, engineers think is high-rise. But generally what the code does is it has different steps from the point of view of, construction requirements and fire protection requirements. And because we are at the point where we're basically above 12 stories, we're into the sort of what typically we like to call sort of the 18-story and above category, we are at 3 hours. And so that, for us, means that we've got to meet the code and meet an equivalent fire resistance to any other building which would be the same height. And so if you're building a 30-story building, in downtown Milwaukee or downtown city and anywhere in the US, and you want to put that structure up, your columns and your beams are going to be 3 hour rated. And so all we're doing is saying, okay, that's the code. We need to be able to make sure we meet that, and we understand what that barrier is as such, and we know the technical difficulties in being able to get there. we need to be able to design to be able to get to that 3-hour fire resistance.
So no matter what the material is, whether we said, hey, we want to build concrete, steel, mass timber, hybrid, we would have to meet these code requirements regardless.
Yep, they are material independent as far as those actual materials to meet the fire resistance. And there are nuances within that. And obviously we have within the code we separate combustible construction, which is timber, versus non-combustible construction, which is steel and concrete. And we have different requirements for each of the different types, but the actual basics of what are the fire resistance ratings that are needed, they are very height dependent and building type dependent. So for a typical office or residential building, once we're at, heights well above 12 stories and well above 18 stories, we're into the 3-hour category for how we need to achieve our fire resistance.
And is it 3 hours everywhere, or is it just 3 hours on primary columns and beams?
It's basically the primary structure, yeah. So, and we define the primary structure as the columns and the beams, so the frame which carries the vertical loads as such. And then our floors are slightly different. So our floors, we're allowed to achieve 2 hours for our floors. And so for the Edison, in some ways it's a relatively sort of traditional structure. We've got a load-bearing columns, load-bearing beams, and floors that span over those. And so we have 3 hours for that vertical structure as such, the vertical load-carrying structure, and 2 hours for the floors. And as you said, would be exactly the same requirements for a steel building or a concrete building that was going up. So those sort of independent of the material.
So it's agnostic of the material from the code perspective, but then why does the code distinguish between this combustible category where you have wood and then non-combustible with steel and concrete? Why is there a difference?
Yeah, and that has a lot to do with sort of the history of the code, and in some ways where we've come from with mass timber. Timber has always been a material which has been in the code. It's been in the code for a very long time. Actually, it's been a material which has been in some ways one of the oldest parts of the code. It was sort of codified back with insurers. We're looking at mill buildings sort of in the 1800s, so it's been in there quite a long time. But as part of that, timber has always been limited to 4, 5, or 6 stories because that was what we could build structurally. So, when you look back in the history of that, steel and concrete were going a lot taller, and timber was sort of, 5 or 6 stories is what we're achieving. And that was where the code is set. So from a history point of view, that is why we've had those sort of lines in the sand. As mass timber has started to change and become a material which can be built taller, we've started to change the technology around that. And that has a lot to do with how we put connections together. The development of CLT, which has meant we've got a nice, efficient floor system. We've been a lot of work has been done on the structural properties of glulam to be able to get those to being manufactured at a larger scale, connected with the forces that are needed for a taller building. We can go to taller heights, and so as part of that, in some ways, timber has needed to catch up. And so part of it is the history of the code, and then part of it is the technology of timber being a very old part of a code, but now becoming something a little bit more modern. And so there's a little bit of history against us when we look at timber buildings, but there's also been a desire to change the code and evolve the code to include mass timber. And so we're in that process of basically wanting to include mass timber, and it needs to meet the requirements that are already set within the code. And that's what timber should do. It's just another building material.
Yeah. So are you saying kind of eventually we're in the progress of getting to a state where this combustible versus non-combustible is almost irrelevant because ultimately it's just if it meets a 3-hour fire rating for primary structural elements, we'll be able to build with timber, steel, or concrete, really agnostic of the material, just based on the code requirement.
Yeah, and that's, in some ways, I'm not quite sure we'll get there in the short term, but certainly in the longer term, that's exactly it. It should be about performance. What is the performance your material needs to achieve? And some codes globally are like that. It's all about, these are the performance you need to meet from a fire resistance point of view and a structural performance point of view, and how you achieve that with different materials. That's up to you, the manufacturer and the producer, to be able to carry out the relevant testing and certification to be able to meet that. And so, absolutely, it would be nice to be in a situation where, the codes are set around, as you say, an agnostic choice, and you can put any material in there and actually have combinations, because in some ways, hybrid buildings as we go taller and we want to have more efficiency in the way we build, is probably the right approach. So you want to be able to swap out materials or have combinations that work for you as the technology changes. So it does become difficult where the code is kind of forcing you into one category or the other, because in some ways, if we looked at a future where we could be in 10 or 20 or 30 years, the materials we're using, potentially, carbon fiber, there's all these incredible nanotechnologies going on. What does that look like? Because, timber's a very old traditional material. It's older than steel or concrete, and it's better having a rebirth, but there's all these incredible new materials which are going to be ahead of us. And where do they fit in? Because, they burn, but, they're stronger than concrete and they're stronger than steel. And, we use them in incredible ways. So where do they fit into the building industry? And that's the interesting next challenge.
I want to circle back on that idea of future materials here at the end. But could you just go into a short kind of story about how we got into Edison, how the entitlements have gone, how the working with the local jurisdiction, especially building inspection, fire department, have been, and what your experience has been, and what we're actually approved under, if it's type 1, if it's type 4. I know there's been some back and forth there, but if you could give a little story, that'd be great.
Yeah, and so downtown Milwaukee, which has been, as it turns out, one of the great cities for mass timber. Ascent Tower was finished there a few years back. It's 25 stories of mass timber. And, the City Department of Neighborhood Services, D&S, have been great. They've been really welcoming. The City Fire Department have been excellent to work with. They are an educated and knowledgeable building department and fire department. They're really good. They're approachable. We can talk to them at any time. They give us their opinion, and they have opinions on the material. They have opinions on the way the buildings are constructed. And working with them through Ascent was, a really positive process. That took some time, and it took sensible amount of time to be able to work through how the building was going to be built, how we were going to put the structure together, and then, how the actual details were going to be built. And so I think the city and, in some ways the construction industry learned a lot from Ascent. And so when it comes to the Edison, this project is, as you know, we've been working on this for quite a number of years, and it's been positive again with the city. We've talked to them about how do we want to make this from the construction type point of view, because that's generally where we start. We start obviously, is it a residential or an office building? How tall is it? And then we start to work out what the construction type is. And the issue in Milwaukee is that from a code perspective, a lot of the country, a lot of the US is on the 2021, or even some of them are on the 2024 code. A lot of cities and a lot of states are actually on older codes. And, Milwaukee is on the 2015 IBC. So in some ways, it's a code which was written, over 10 years ago. And that puts some barriers in our way. And it's, in some ways, it's a little bit like not quite the square peg in the round hole, but it's sort of the square peg and sort of the hexagonal hole. We've got to sort of work a way around to be able to try and fit out how this building works within the code.
Yeah, if we can pause there for a second, just to give kind of listeners an idea of what we're talking about when we say IBC. It's International Building Code.
Yep.
And the reason why Wisconsin is still in 2015 is because there's been a lot of politicization around this idea of promoting into a future code, because there's a lot of lobbyists that want to stay in an old code, because like single family home builders in Wisconsin, obviously if they keep it in an old code, their building is typically cheaper. And so they, of course, want us to keep us kind of back in this antiquated state, which I'm totally against. I'm like, one, for life safety, it's not great.
No.
Two, it's like we have now almost 10 years of code editions that have been published that we're not adhering to any of them. And we're living in like basically this stasis state of 2015 for the last 10 years. And it like makes absolutely no sense to me.
Yeah.
And I think it's like, I would love to hear your opinion on if we were in 2024, how that might change some of these entitlements and some of the codes that we've been running through while you're going through the story. But I'll let you keep going.
Yeah, no. And I totally understand your view. And it in some ways it does, I totally understand. It becomes frustrating, and partly from our point of view, because, standards, especially standards that are referenced in the code, sprinkler standards, alarm standards, standpipes, everything like that is referenced in the code. And so the question then is, often you're using a standard which can be 10 or more than 10, sometimes 15 years old, and the technology keeps on changing in fire protection, and our ideas of what potentially can go wrong keeps changing. So we want to keep improving standards. So in some ways, we're all stuck in this problem with the fact that we want to use the most up-to-date standards because they are the safest standards to be using, but we're stuck in a situation where we can't quite reference those. So that's a continual negotiation with the city, because we want to be able to use the most up-to-date versions of codes and standards. That's the best we can do. But we recognize that the city has a limitation around what they can do. So that definitely becomes a problem from our point of view. So certainly from a code perspective, we've had to continue to work with the city to be able to work out, how does this building fit? And under the 2015 code, a mass timber building could go to 6 stories. And so, that's the limitation in the code. And everything started to change basically from the 2018 and 2021 versions of the code. IBC is issued every 3 years, and we do updates every 3 years on a continual process. So we had updates in the 2018, but we had some significant updates in the 2021 code where we introduced high-rise mass timber construction, and that was a big step change. So we introduced 2 new construction types, which allowed us to build not just to 6 stories, but to 12 stories, and another construction type that let us build to 18 stories. So that was a major change.
Dave, just pause right there. Why was that change finally adapted and adopted into the code? And what was all the kind of previous testing that had been going on before that to actually allow the IBC to introduce tall timber?
Yeah, it's a long story. Won't go into too much of it here because it is a long story. It's a great story.
We have time.
Well.
We have another hour and 30 of the test, so we have plenty of time.
That's a good point. We do. We probably would take that long. It's partly driven around the fact there was 2 parts of it. One, there was some really tall, very innovative projects that were going on in Canada for timber, and there was a lot of people in some ways in the US looking at those and wanting to look at saying, well, how can we adopt those? And I think one of the real key aspects of that was around 2013 there was a competition called basically the tall mass timber or tall wood building competition, which was launched by the Softwood Lumber Board. And as part of that, they awarded two prizes, one on the West Coast in Portland and one on the East Coast in New York, to 2 basically brand new timber buildings which were going to be high-rise. One was going to be 10 stories and one was going to be 12 stories. And part of that was to help to do 2 things, to sort of be the case study projects for how we could design high-rise timber buildings, but to also then be projects which could be funded to help do some of the background testing and help sort of push the industry along that we could do this. So, and as part of that, also separately, but also, partly as a spin-off to that, there was a new code committee formed to look at changing the code and aiming for the 2021 building code to make code changes. So between about 2014 and about 2018, 2019, there was a whole lot of things that went on. We were doing some large-scale testing. We were doing some large-scale compartment testing. We were doing, element testing. We were doing connection tests, and we did our first ever connection test for the framework building, which was one of the tall wood building competition winners. And that was a significant change, and that was, again, a step change and helped prove the fact that mass timber could meet 2-hour fire ratings. And we were doing research testing as well, where we looked at larger compartment fire tests, and they were funded by the Forest Products Laboratory, USDA, US Department of Agriculture, and with the ICC, the actual organization that helps write the committee, helps write the building code, part of the committee that were actually writing the code. All that testing that was going on in the background, and then the code committee were taking that. There was a lot of testing that's been going on and funded in Canada as well, which played a role in helping to facilitate and educate everyone in the US as well. So in some ways it was a North American effort at helping to get the codes, the evidence that was needed to help change those. And so there has been, when you look at the background, just in North America alone, there was an enormous amount of fire testing that went on, larger scale, medium scale, and smaller scale, that helped build the case to change the codes here in the US and in Canada as well. And that was, a significant period of investment. And it's had some, enormous benefits in the code language, which we see now.
And that's what's kind of unlocked this ability under Type 4 in 2021 IBC to build in kind of this mid-rise / low high-rise prescriptively.
Yeah.
And I know you helped us on Baker's Place, our Edison Project, which is 14 stories.
Yep.
Which is entitled under 2021 Type 4B. And so I think it's been fantastic. Like, we went through that. We had our challenges, as you know, with the city of Madison, but we did get our approval and we got to build that building prescriptively, basically under the code. So all that work leading up to that event, I think, was really promising.
Yeah.
And so
totally agree.
maybe talk a little bit more now that we're jumping back into the story on Edison and just how we're getting approvals there.
Yeah.
So we started in 2021. We're a smaller building at first. We were going to be under type 4. We grew the building a lot. Tallest mass timber building in the world. How has the jurisdiction reacted to that? And what's been the leading steps now up to this test? And then what's beyond the test to actually get final approval?
Yeah, I think we've continued to work with the city, and it's you say the building has grown, and we've continued to work with the city as the project has changed in some ways, and it hasn't changed too significantly. We obviously changed the height, which was an important change, and we also have worked with the city looking at the construction type, because one option is you can with a building like this, which sits in some ways right outside the code, because at the moment, under the 2021 code or even the 2024 code, we would be at 18 stories is where we can max out for mass timber. So we are, well above that at 32 stories. So we are sort of outside the code anyway. So we've always been in a situation where we know we're outside the code. So how do we work with the city to be able to look at what are the fundamentals? And so there's been two paths on that. One is that how do we permit the building under the current 2015 code as a type 4, so as a timber building. So type 4 construction is timber buildings. And so that's always been one path, and that's, has its difficulties because, as I said, that's limited to 6 stories. So that has a whole lot of challenges, but in some ways it kind of makes sense to do it that way. The other option is to look at it as, in some ways, a concrete building or a steel building where we could build a lot taller. So we could build this, if you were looking at building a concrete or a steel building, there's a construction type called 1A, which allows you to basically build an unlimited height. So you wouldn't have any restrictions on height. And that would be the other option, to do that and to be able to say, well, we look just like a 1A building, but our structure is actually part concrete and part timber. So, that we could look at changing and stepping outside the code and using that as sort of a starting point. And so what we've done is look at both of those starting points and work with the city as to what is the better option for them. Because in the end, we've got to, they have to agree, with us as to what is the best approach. And at the moment, we are looking at more the type 4, so looking at it as a timber building. So from a code perspective, how it's permitted, it says it will be a type 4, which is a timber building. And so that's how it's going to stay. And I think, from our point of view, the end point is the same. It's just we start at different locations, and you kind of take the journey to get to that end point. So.
Yeah, I think about it, I do a lot of mountain climbing, and I think about it, you can climb from one side of the mountain or you can climb from the other.
Yep.
But either way, you're going to hit the summit at the top.
Yeah.
And it's like on this one side, we have type 4 construction, and on the other side, we have type 1.
Yep.
And the thing is, from my understanding, neither allows us to prescriptively build this building.
Yep.
Either way, we're going to get variances, alternative means and methods requests. And so it's like, what kind of dragon do we want to slay in order to get to the top of the mountain here?
Yep.
And so from your perspective, kind of what has that path been now that they have given us some direction about us going with the type 4, and how do we get to the summit of the mountain?
Yeah, and it's in some ways there's some obvious things like the building height, the number of stories, and just the building area, because even though the residential building on a floor plate size is not huge, there's a limitation to the amount of floors we can build in the number of areas. So there's some pretty basic sort of building block type things like height, number of stories, and area, and they're obvious things, and we can deal with those from a city point of view in some ways by saying, right, we're stepping out of the code and looking at this from a fundamentals point of view. And there's some intricacies, because type 4 is a very old part of the code. It's been there for a long time, so it's got some funny sort of aspects. Like one of them is the fact that you can't have any of the timber concealed, so we actually have to have all the timber exposed, which and to a lot of people who are involved from a fire point of view with mass timber, generally as we get taller, we want to basically protect the timber and put protective boards on the timber to stop it basically catching fire, and so it doesn't become part of the fire. So the old part of the code says, actually, no, we don't want that. We actually want to have it completely exposed, and you can't actually put any sort of ceilings into place. So it from our point of view, it's kind of like, okay, we can use that, but we've got to understand why that's in place. And part of that was driven around, we don't want to have fires in concealed areas. So it's all about, can you have a fire in a concealed space which can spread and cause problems? And that's an understandable battle. So part of it is, what is the code requirement? What is the fundamental aspect that we're looking at? And then trying to work out, okay, and then how do we actually protect our building and design that out? So we're looking at trying to have protection for all the concealed spaces. And some of those are large, like, we've got spaces where we're, 6 inches or so drop ceiling. We've got a protection on those. And then we've got areas where we've got, an inch or so, or less than an inch of space between a wall and a column. So we've got a vertical concealed space. And how do we protect those? So we're going through that detailing now. So that's the sort of things we need to look at. And there's a few other little intricacies in the code because of that, where we say, okay, what is the issue? How are we meeting those? And then there are a whole lot of parts we're exceeding, because type 4, because it's low-rise building, we're basically saying, well, we're going to have the same fire ratings, the same fire protection we would for a typical 30-story building that was constructed of concrete or steel, down the road. So if you had another 30-story building across the road from the Edison, what fire protection would go into that? And we're going to have exactly the same fire protection, and we're going to have some additional fire protection because of the way that we're treating some of the aspects of mass timber. So it should be exactly at an equivalent level to any other residential high-rise building, 30-odd stories or whatever it may be. But we're also saying, okay, there's certain things we need to have additional fire protection in because of the fact we've got mass timber, and we need to deal with that.
And can you give us some insight into what that additional fire protection is? Because just going back to where we started with this conversation, you're saying that we're meeting equivalency of steel and concrete.
Yep.
From the rating side. So someone living in this building doesn't have to worry about the building being less safe. It's just as safe as concrete and steel, and it sounds like it's actually even more safe. But what are we doing as those kind of additional benefits on the fire side? Yeah,
and there's a few things we're doing. I mean, one of them is we're actually, in some ways, we're proving the fire ratings, i.e. we're doing fire testing, because, and we need, in some ways, there's two parts of that. One, we need to be able to prove the fire ratings because we've never done this before, and no one's done it, and we can't point to a test and say, well, this has been done 10 times before. So one of the things is there's a level of, in some ways, safety and knowledge around the fact that we have tested this, and we have tested it on exactly the same structure that we are building. So that is a replica of what we are building. So there's a certain amount of, in some ways, level of additional resilience in the fact we're testing what we build, which doesn't happen. Most buildings, we don't test what we build. So that's one aspect. And then the other part is we're looking at what additional measures can we put in place that make sense from a firefighting point of view and from an evacuation point of view. And one of those is the fact that residential buildings have a lot of walls. And so we have all this sort of compartmentation which just sits in place. And what we're doing is making that, in some ways, more resilient against fire. So the walls that go between every residential unit, there's a minimum level of fire resistance they need to be. And typically that is normally 1 hour. And so we would put a 1 hour wall, and obviously any penetrations or any holes in those, we fire seal those. The door is fire rated as well. What we're doing is we're increasing those. So we're basically putting 2 hour separation around all the residential units. So each unit has an additional level of protection. And what that does is it means that if the worst case, we do have a fire that sprinkler protection doesn't go off like it needs to for some reason, very unlikely that it wouldn't. The sprinklers are incredibly reliable. If the fire department for some reason are delayed and aren't able to get to the fire for some reason, there is an additional layer of safety in the fact that the fire can't get out of the residential unit. And so we're not expecting a fire to actually last much more longer than an hour anyway. But if it does for some reason, then it's not going to break out of that unit. And so that allows us from working with the fire department for them to be able to say, okay, we've got this additional protection of the actual resilience around the spaces that in some ways gives them more time and gives them more space to be able to fight a fire, because they know that they're not going to be in a situation where if they were delayed, the fire may have broken out as potentially in a corridor and they have to fight it from a stairwell. They actually know that it's going to be within the unit itself. So those are sort of things which I think are really important. There's additional things as well we're doing. We're improving the resilience of the water supplies to the building for sprinklers and hydrants. And that helps from a reliability point of view, because, if we've got the water supplies we need to to be the first line of defense against a fire. If something does go wrong with those, often it's not in the building, it's often on the street, and it's related to how the water gets into the building. So we're improving that. And that is a huge benefit for the building generally. And not all buildings need to do that. But when you get to a certain height, we start to improve the resilience of the water supplies. And we're doing that for this building as well.
And a part of that improvement, my understanding, also includes 2 water supply.
Yep.
And so if one ever went down during a fire, which sometimes my understanding, which this is kind of scary, that sometimes we only have 1 water supply on high rise.
Yeah.
If it's concrete or steel.
Yep.
And so in that event, if we have a fire in a concrete or steel building and you're living on the 40th floor and for some reason that single point of failure decides to fail on that day that you have the fire, I mean, you're not in great shape, right? Because it's like you don't have your first line of defense for the fire, which is your fire
I mean, we still
sprinkler
have,
system.
we still just, we still have a lot of lines of defense in buildings from a fire point of view.
Yeah.
In some ways, high-rise buildings are really well protected. There's always this line which I think has been great, which I've heard, people say that, some ways we put fire protection into buildings and they're very safe. And then as we get taller, we put even more fire protection in, fire protection being structural protection, alarms, sprinklers, all those sort of things, and they become very safe. And as we get taller, we actually become very, very safe. And that's exactly it. We put on more and more additional layers. And we've learned that because we've had some really catastrophic fires, and we continue to see other, unfortunately, catastrophic fires occur in high-rise buildings. And we can point to the failures, and we can look at where in the code, in some ways, we have learnt from that, made the changes, codes and standards, and improved on the fire protection. And so, you are right. We have lines of defense, and we want to be able to make sure those lines of defense are very good. But also we have, backups, and we have additional measures to be able to make sure that we absolutely protect buildings from a fire safety point of view. And water supplies are an important part. Fire resistance is an important part. And then, all the other measures such as fire alarms for alerting and, the ability for firefighters to go into a building and take protected elevators up to the floor, up near the fire origin. They can go to the floor below and they can get access straight away with all their equipment. And we put those in buildings. We put 2 firefighting elevators into a high-rise building, absolutely incredible access for them that are protected so they can actually access a fire floor below if they want to, 2 floors below, and have their equipment there, which is just as important, and get the manpower there, person power there to be able to fight the fire.
And what do you mean when you say we have 2 firefighting elevators? What's the difference between a firefighting elevator and just a normal elevator?
Yeah, there's a couple of things. Part of it is size and dimension, but importantly, it's they are basically protected into a space where the lift shaft and then the enclosure, the lobby around it is fire protected and fire rated. And then it's accessed from a stair as well, so that basically we have the protected stairs. So if you imagine from a firefighting point of view, if the worst comes to worst, the firefighters want to stage from 1 or 2 floors below, and they want to be able to then access to be able to fight the fire on the fire floor. But they want to have for the people there, the crews there in the right number, and they want to have the equipment there, and they want to have the right amount of equipment. And so the ability to have that in an elevator, which is slightly oversized, rated for a slightly higher weight to allow that equipment, it's protected, has backup power supplies as well, so it's a really resilient elevator, means that they can come into the building through a protected path, access that elevator, get to the floors they want to be able to fight the fire, and it cuts out that whole issue of firefighters having to access things through stairs.
Yeah.
And there's always this sort of argument that that's sort of is an important part of fighting fires, is to be able to access stairs. But what you want is the people to be able to evacuate down the stairs. And you don't want the issue of firefighters with their gear having to go upstairs when people are trying to evacuate downstairs. And you want to be able to do that in the most efficient way. So if we can somehow separate that counterflow by having firefighters and elevators going up with their gear, allow people to come downstairs in their own pace. It's it's absolutely fire rated and fire protected space. It's ventilated and over pressurized so the smoke doesn't come in. People can take time, and we're dealing with people who are elderly. We have people who maybe mountain climbing and fall off the mountain, got a broken leg.
Yeah.
You may be fit and healthy today, but you could be terribly slow tomorrow.
Yeah.
So unfortunately, and that's the problem. You've got people who able-bodied, but then a week later may not be able-bodied, and so how do they get down the stairs? And you want to be able to allow them to do that in a pace, which means that we can do that and allows the firefighters to do their firefighting in a way which is efficient and makes sense.
Okay. And so just getting back to our story about finishing the entitlements on Edison, what is kind of, after this test is over, what is the report going to be that you get? And we're going to interview Josh here in a little bit, who is our structural engineer, is going to get. And how are we going to take that to the city and kind of show them that we meet the equivalency of type 1 construction with concrete and steel?
Yeah, and there's a bit of work for us to do that, and the fire testing is part of that. So, we're doing fire testing as we talked about earlier, to be able to prove that, what we are building and what we are testing works. So that's one of the items as part of that. And as we talked about earlier, because no one has done that before. So this is brand new, this is innovative, and this is, right at the cutting edge of being able to construct a building to the code and making sense of the fact that we want to have the elements that are going into the building that we've tested. And it's, it's good for you, and it's good from my point of view, and it's good from an engineering and architectural design point of view that we have, in some ways, we have the right tests in place for that. So we have fire test reports that go as part of one of the reports that I take to the city, which is basically, here's all the structural elements and how we've tested those. And there's in some ways, there's a list of standards we need to meet that the code requires. Again, completely agnostic of the material, and so we need to meet all those. And so we're going through the process of, in some ways, meeting all the standards and providing all that information for the city. And we've known about that from the beginning of this project. So this is all about, we've known we need to meet all these. Let's go through that process, and this is, in some ways, the end part of a long journey to do that. And then there's a second part of the reporting from my point of view, which goes to be able to prove that we can actually design a timber building to 30 stories, 33 stories, 32 stories in this case, and do that in a safe way with timber. And so part of that is me being able to show that as a building from a fundamental point of view, it stacks up against steel and concrete. So what we do is basically we look at the fire ratings, and we look at all the fire protection systems that are going into the building, and we look at things like evacuation and firefighting and how those will interact in this building compared to a typical, code compliant steel building. And what we're doing is we're doing an equivalency to be able to say, this is our building, this is potentially a neighboring building of the same shape and size. What would that have and what would we have, and how do we meet that? And in some ways, the difference is that we've got timber in this building, so we have a slightly different fire. We have a fire that would be different than the fire we would have in a residential building where we don't have mass timber. And so we have to account for that. And that changes the way that the fire burns within a residential space. And so we're basically analyzing how that fire burns. And we also have to look at how that impacts potentially, if everything, all the fire protection goes wrong, the fire department are slow to turn up, how that affects the structure. And then potentially also things like how do flames coming out, because when we have a really bad fire, we have flames which basically leave the building. How do they impact other units around the building? And then also sort of some basic fundamentals like, does the fire department have enough water? We've got a bigger fire. Do they have enough water to be able to deal with that fire? So those are the sort of checks we also run to be able to make sure that we've got a building which is safe.
What do you mean when you say when we have a steel building or a concrete building of equivalency, those buildings, when they catch on fire, those fires burn differently than when we have a timber building that catches on fire?
Yeah, and that's all to do with the fact that we are exposing some of the timber. So if we wrapped all the timber in like fire-rated boards, in some ways the timber wouldn't see the fire. The fire would look just like a fire which was occurring in a steel or a concrete building, a non-combustible building. And then, as soon as we start to expose the timber, we're changing the fire slightly. In some ways, residential fires, we can make an assumption about what's in the space. There's a certain amount of TVs, certain amount of couches, certain amount of beds, certain amount of stuff that everybody has. And we know that. And so we can work that out. And we've got a good idea of what that looks like. And we've got a good idea of what the variance is on that. But the part that changes things is when we expose the timber. That timber, when it burns, actually adds fuel. So we're converting the actual mass of the timber, the actual structure itself, and we're turning that into fuel. And so it actually adds to the fire. And what it does is it doesn't change the temperature significantly. It doesn't change the fire growth a little bit, but not too much. It just changes the duration. And so if you imagine it's in some ways it's looking at it, and I've had to explain this to sometimes to building officials who have never seen this before, and we've had to show them videos of tests and examples of where we do this. What happens is if we change that amount of exposed timber, we look at extending the fire duration. And so the fire basically grows and it peaks because sprinklers don't operate. We don't have any fire department intervention because that's what we want to design to. We want to design to sort of the worst possible fire we could come up with. And then we look at what the changes, what their difference is in a fire. So a fire in a non-combustible steel or concrete building, and then a fire in a timber building. We want to understand that difference. And then we want to work out, okay, then how do we design for that difference? And in some ways, it is an engineering problem. I mean, there's a lot of engineers out there who have to deal with different problems. Seismic engineers have to deal with buildings that go sideways and go up or down. Wind engineers have to deal with vibrations and lateral resistance. Geotechnical engineers have to deal with ground conditions which change. From a fire point of view, we have to deal with a building which has a different fuel condition and a different way that the fire burns. So we have to account for that. And it's all about how do we account for that and how does the structure respond? So, and the difficult part with timber really is the fact that as the timber burns, it changes the fire. But if we change the fire, then that impacts the structure. So it's sort of a circular aspect, which we don't get with concrete, because concrete or steel, non-combustible buildings, when the fire is burning, it's the fuel and the structure is basically inert. It doesn't change the fire. So the main difference is the fact that when our fuel burns, which is what's, the TVs and couches and sofas and everything, plus the timber, when that changes the fire, that changed fire then impacts our timber. So it's sort of something we have to work on to be able to work through that and then understand how that fire basically changes the way that the material behaves. And so that's part of the process. This helps. And then we look at different sorts of fires as well. We look at a range of different possible fires that could come into that building.
So let's just pause here on this thought for a second, because we're starting to get into this kind of concept of char. And I think it'd be helpful for you to just explain what char is and how it relates to this idea of you have, your furniture, all your different materials in your unit. And we did a test 2 years ago at USDA Forest Products Lab where we test for flashover, which is what you're talking about.
Yeah.
And I think that was really helpful for us to understand how the things that we do have from an exposure standpoint affect the fire and the fire spread. But maybe just explain, back up elementary style, what char is, how it impacts the fire spread.
Yeah.
And then how that relates to some of these calculations that you do where the mass timber is adding fuel to the fire that's burning.
Yeah. Well, and speaking of warm, it's getting warm in here.
I know. I'm sweating. It's a lot.
It's like I need to turn a fan on. So it's good. It's what it should be happening. So, we've always known with timber when it's exposed to fire that what happens, whether, best way you can think about this from a wildfire point of view, when a tree is exposed to a wildfire, basically it catches fire and it burns, but it chars. And we see that. And when we put logs on a fire, it starts to burn and then it starts to char. And that fundamental aspect of how a tree protects itself from wildfires, which is what's happening, the tree is protecting itself by charring. And by doing so, it's basically an insulated layer. So it's putting on basically a blanket, and that's a thermal blanket, and it protects the inside. Because timber retains its strength and retains, in some ways, a tree retains its life by the moisture that's inside of it. So by having the charring, basically it's protecting the inside where the moisture is. And then, we see this with wildfires. If you go back after a wildfire 5-10 years later, everything's regrowing. Most of the trees which haven't burned through, they've built the outside. Some of them don't even look like they've been through a fire. They've completely regrown. You often see the lower parts of the trunks are still black, but a lot of new growth. And it's incredible the way that trees and forestry can regrow after a fire. Well, that natural process we use for timber structures. And so what we want to be able to do is understand, and we do through testing, how timber members char. And that charring occurs at a certain rate when we put a certain fire against it. So what we do is we say, okay, let's have a certain fire we put against a timber beam, say, and then we measure the charring for that certain fire. And so what we do with that is then we're able to then estimate based on this fire what the actual depth of charring is, the protective layer. And so we then use that from an engineering point of view, because in the same way what we do with concrete is, for a concrete member, we have steel reinforcing in it. The steel reinforcing gives the concrete member its strength. So we actually put the reinforcing bars inside a protective layer of concrete to make sure that they're not affected by fire. For a lot of steel work, we wrap those in sort of spray protective measures, or we put boards around them. Again, it's an insulated layer that helps protect it from fire. And so timber just does that naturally. And we can do that by putting boards on it if we want to add or we can use the actual charring itself. And so as timber is exposed to longer fires, we get a deeper charring layer. And so we're able to use that to be able to reverse engineer how much timber we actually need to have left at the end of that fire exposure to still carry the loads. So for a column, say, we know that it needs to be a certain dimension to carry the structural loads. What we can then do is we can add additional timber to that additional area, which is then sacrificial. That would then be in some ways charred off and removed in a fire. So what's left is the column that actually carries the load. And we've been doing that for, probably close to 50 years now. It's a process whereby a lot of that research was done here in the US and in Canada, looking at how timber chars and understanding how it chars to what is called the standard fire. And the same standard fire is the same fire that's in that furnace. And it's a standard fire we use globally. So in some ways, it's the same measure. It's like having the same wind against all buildings, the same sort of seismic event on all buildings. We have the same sort of fire standard which we can use on buildings. And it relates to potentially how a building fire would actually burn, but it allows us to measure relative material differences. So we use that same standard fire for all materials. And so that's why we use that and measure how char actually affects and protects a timber member.
And I know for this, we did a pre-calculation to determine what the char would be.
Yep.
Can you talk about how that calculation, what goes into it, and how you determine for what we need a 3-hour column, how you figure out how many inches of sacrificial wood you need to put on our column in order to last for 3 hours?
Yeah, and as I said, we've been doing this for, in some ways, decades. And so we have a good idea of what happens when we expose timber to the standard fire. So the fire which is in that furnace at the moment, which is a standard time and temperature curve. And so we know what that rate of char is. And we know that for every hour, we get a certain thickness of charring for every hour. So based on the standard curve, and it's codified, it's actually in the code, we've got basically, for every hour, we have 1.8 inches of charring we need to basically remove the sacrificial layer. And as part of that, there's a safety margin within that as well. So we've got an engineered value and we've got a safety factor that sits within that because, engineers, we like safety factors. We like to make sure we have as many good safety factors as we can. And so the code at the moment used to only have 1 hour fire ratings in it. And then we've increased that to 2 hours because we've gone taller. And so we've said, okay, we've as talked about earlier, as buildings get taller, our codes and standards need to change. So we've gone from 1 hour to 2 hours because most of our buildings sit in the 2 hour range. 3 hours is different. So we actually don't have a codified value for 3 hours. And so we initially did some testing for Ascent a few years back where with the Forest Products Laboratory, which is a federal research facility in Madison, we actually did some small scale tests looking what would happen if we exposed timber to 3 hours to basically measure the charring and to see that does the charring rate follow the same correlation that we've got in the code now. So, in some ways, the line we've got is a mathematical correlation that goes with that, and we can, for any minute, we can work out how much charring we've got. It stops at 2 hours. So what we did was we took that to 3 hours and then checked it with some additional testing to basically just make sure that we were okay. We were all pretty sure that between 2 hours and 3 hours we would have exactly the same values that we would be able to calculate, and we did. We actually found that we were, in some ways, that it performed better in the testing than it did from our calculations. So we were happy with that, and so we've actually then used that and then used analysis as well to be able to look at what is the expected thermal penetration, how much does the heat actually get into the actual timber member for 3 hours. So before we've done testing, we've actually kind of analysed to work out what it should be. So we've got an idea of what it should be, and we've in some way sized the beams, sized the columns, sized the connectors on our numbers, and again added a little bit of safety to that because we can, and we know we've got the space to be able to do that. And that's helped us to inform to make sure we get the tests as successful as we can.
And so just to talk about this for a little bit, is this test here is actually completely new, really revolutionary, because no one has actually assembled a full column beam and then put a top on it with CLT and tested the full assembly, right? It's only
to 3 hours.
To 3 hours, right?
Yeah.
It's only the only 3 hour test as of right now is the very small one that Ascent did, where they just tested a small column to see how long the burn really was, right? To basically quantify and assure that your calculation was correct.
Yeah, that's correct. And so there, 20 or 30 years ago, there has been some 3-hour tests around. Most of them aren't published, and some of them, I've tried to find those, and generally they're sort of experimental tests that have been carried out. But realistically, when it comes to exposed timber and actually having exposed timber burn for 3 hours, very, very little has ever been done. And this is a loaded test, so that's different. That's the first time it's been done, and it's a beam to connection. And generally, we kind of start with things like beams first because they're easy.
Yeah.
But we've kind of gone and pushed the envelope a little bit and gone for a beam to column.
And so with this loaded test, could you just talk about what it means to be loaded, why it's loaded, and what that means for the building?
Yeah. And so within the test, as I explained earlier, we've got a beam and we've got a column. And you can't see the column, it's in the furnace, and you can see the end of the beam, and you can see the CLT floor, which sits on the top. And above that is a loading jack, and it's sitting on a rather large I-beam, which then helps just to close up the space. And so what we're doing is we've got the column that would actually go into the Edison. We've got a beam which would go into the Edison. And what we're doing is we're looking at the loads for a typical floor and applying the load and just slightly more. So we're actually applying more than what the actual connection would undergo when it sits in the actual building. When it's actually fully constructed and the building is fully operational, you put everything inside the building. So we're putting on a little bit more load than we need to because, it's always good to do that. And so that absolutely replicates what the building will be constructed with. It's the column is the same, the beam is the same, the CLT floor, and we're applying the load that would actually go into the building.
And this allows us then to replicate, say, we got a fire. Hopefully we don't, knock on wood, I don't have wood, but we have a fire on the 20th floor of Edison, and we have a column that's burning. This replicates that exact column and beam condition that would be burning so that we know how long that beam and column connection will last in a safe way.
Yep.
And is that something that a lot of people do on all their buildings, or does a lot of developers not spend money on that?
Very few do. In some ways, when you're a code-compliant building, you don't need to do any testing. And so most buildings that are constructed don't do any testing because there's no need to. When you are stepping outside the code, maybe a small amount, you may look at some engineering to be able to look at something which is slightly different. When we're quite a long way out of the code, as we are for this building, we then start to have a look at, what testing and what information is available to us. And when there isn't any, we've got to do it ourselves. So, you're in the situation where you're really, pushing what mass timber can do. And so we're looking at it going, okay, where are the gaps? And then how do we fill those gaps? And how do we best assure ourselves as a design team? And then how do we best assure the city, who have to provide us with a building permit, that we've done all we can to basically fill those knowledge gaps. And so this is part of that, is filling the knowledge gaps to be able to understand how it performs and then, what the expectation is. Because part of it is that, from a building point of view, we don't ever expect the fire to ever get close to 3 hours. We're putting it through a 3-hour test because the code asks us, because it's a tall building, to have 3 hours. Now, in the building we've got, we would never expect the fire to last that long. And it's one of those things whereby, from a historical point of view, there's always been a reasonable factor of safety in how we design for fire. And so in some ways, we want to have over-design the loads that we put on, so we know we're never going to have as much load as that. And we want to make sure that our fires that we're, in some ways, everything is being tested to, are worse than what we could ever imagine could go into the building. And so we've looked at what the worst case fires are in the Edison, and also we did that for Ascent as well. And we've got a good level of safety in the fact that we know that this fire is significantly longer than what we would expect the structure to be exposed to. And we have always done that for building structures. That has occurred in the 80s and 90s, and it's continued to occur as we've innovated with concrete structures and steel structures. So in some ways we're following a bit of a well-trodden path, because as we continue to innovate in construction, we continue to look at, okay, we're doing something innovative, how do we test that? And so part of that is, we've got in some ways a bit of a recipe book about how we test and what we test to, because in some ways there's been a whole lot of other innovative structures that have been built over the last, in some ways, 30 or 40 or 50 years, which were built taller and built differently, where we've had to do different tests. So we can look at those and say, okay, what is the best way to be able to test? And that's where we talk with the city. Look, work with the city to say, right, this is what we think we should be doing. They have opinions on this well, and we work with them and come to a collective opinion as to what is the best way to be able to test.
And so once we finish this test, and we have a few more tests after today, what will be will that be the final approval point that the city says, okay, you guys are good, you can build this building?
It should be, yeah. We're at the point where we're kind of at the nitty gritty end. We need to pass these. We can see the daylight at the end of a tunnel. And so we've still got some work to do, but a lot of it's, if we pass all these fire tests, a lot of it, the rest of it is just, in some ways, the paperwork that we would normally need to do to be able to get a building approved. There's a lot of detailing that needs to go in to be able to provide that information. And as you know, from a design point of view, we've still got work to do on that, and there's a lot of specifications and details that need to be sorted out. They will all get done. But yeah, we are some significant steps towards getting to the point where the city will say, yep, this building is ready to go.
We're good. So out of 100, you think we're like 99.99% there?
Probably more like 95. But 95 is a good number.
But once we pass the test, then it's like 99.
From a fire point of view of the hard work, we're like 99. Like, this is the hard work. So it's like
nice.
It's like mountain climber, the Hillary step. The Hillary step.
We're just about to the summit.
Yeah, this is our Hillary step on Everest. So if we get over this, the rest of it's just a gentle climb up to the rest of Everest. So
really?
I
want to end. I know we still have a little bit of the test, but I want to end on a story.
Yeah.
We have been leasing up Baker's Place, which is the project in Madison. For those who don't
which
know,
is looking good. Well, I was in it last month and looking really good.
Oh, were you?
Yeah.
That's great.
Yeah. Well, you were in New Zealand. I was out looking at your building. So,
yeah, nice.
Well, I was working. You were.
We probably passed each other halfway.
Exactly.
In the
You're
Pacific.
enjoying yourself.
Yeah. And so we've had these tours because we're doing leasing now.
Yeah.
And so we had a mom tour a student, and they were walking through the building, loved the design, loved the amenities, but they're like, we're really concerned about the wood.
Oh, really?
I don't know what's going to happen here. And she was really worried about fire. She was like,
oh, wow.
My daughter's going to be sleeping here. There's exposed wood everywhere. She's going to be on the 10th floor. What if it burns?
Yeah.
Is she going to burn in the building? And so, of course, our property managers were like, no, it's completely safe. It's been designed to code. Everything's going to be okay. Trying to kind of ease minds.
Yeah.
But from your very technical perspective, what would you kind of respond to that panicked mom about her daughter potentially living in a wood building?
Yeah, well, I think the thing is I would live in the same building. I'm fine with that. You're probably, in some ways, one of those things. I think, from my point of view, they're very, very safe buildings. And we have, in some ways, because timber is in some ways relatively new, we do have additional layers of protection within timber buildings. And I think that's totally reasonable that we should. We've got new technology, and all new technologies, we need to kind of be pretty cautious around it. So first of all, there is some, really good fire protection and really good safety measures in that building. And in some ways, as part of that building, part of the design of that building as well, we are using, in some ways, the most recently tested technology from a building point of view. Everything that has gone into mass timber buildings that are, in some ways, mid-rise buildings, we have done that testing the last, realistically, 5 to 10 years. So, it's not something which was, in some ways, tested 30 years ago or 40 years ago. And I think that's important. And it's, in some ways, maybe not everybody understands that, but I think it's the difference. And I look at it from a point of view, if you were driving a car and trying to decide on a car, you want to be able to have modern, very new safety measures, and that's what we've got in that building. And we've designed it to the most recent codes that have allowed for the most recent fire events that have occurred and have mitigated for those. So I think having buildings which do have timber is perfectly safe, but also they are modern buildings, and I think that's really important, is the fact that they are up to date with the way that we build current standards, current codes, and that's an extra level of safety in itself.
Yeah, I mean, just going back to where we started with this discussion about codes and how Wisconsin is still in 2015.
Yeah.
I mean, we built Baker's Place to be in accordance with 2021.
Yeah.
So really, any other building that mom is touring with her daughter in Madison would be 2015 code,
exactly,
and it's like there's a lot of unsafe factors in there.
Yep.
That
That's
could
exactly
potentially
right.
be an issue.
Yeah, and Baker's Place is a good example. We worked with the city and actually said, well, we would rather use the more up-to-date code because it's a better code and it offers better level of protection. And I think we got good feedback from them because they said, yeah, well, you've got you're going to use the most recent sprinkler standard, the most recent alarm standard, the most recent standard for, emergency lighting. So they were on board with that. Then they agreed, yeah, we should be using those most up-to-date standards because all that protection, all that, infrastructure within the building, we want that to be as modern as it possibly can. And that's a really good, I think, example of where the city can look at that and be, in some ways, it's always a difficult problem for them, and I completely sympathize with them, the problem they're stuck in with an old code and having to have modern buildings because it's a really difficult position. But I totally agree. We want to be able to build to the modern standards.
Yeah, for sure. Well, thanks for coming on.
No, it's great.
This is exciting.
Yeah,
it's a
cool.
new venue and hot but fun.
I know. Who would have thought sitting in front of a fire test is burning away in the background?
Yeah, exactly.
I have noticed that there's been a little bit more protection going on around the end of the beam there because we typically get a little bit of leakage there. So that happens. That's expected. So
yeah,
it's looking okay though. So how long we got? Maybe an hour and a bit to go.
Yeah, it looks like we got another 40 minutes. So in 40 minutes, we'll find out if we pass or not.
Yeah, that's
We'll make sure to add it to the end of the podcast session so you don't leave on a cliffhanger.
Yeah.
But thanks for joining.
No, thank you for having me.
Glad that you came over from across the big pond.
Yeah. No, it's great. It's great to be here.
Safe travels back to Melbourne.
Thanks, Nate. Thanks very much.
It would be hilarious if that actually did light on fire and we had to run. I would just grab the SD card.